Good morning, all of you. Today, I am going to make an audio recording for visually impaired student of organic book of Dr. J.M. Sehgal, modern book. Name of the chapter is cycloalkanes. Introduction. Cyclic aliphatic hydrocarbon or alicyclic hydrocarbons are the hydrocarbons which contain closed chains or rings of carbon atom and resemble open chain or aliphatic hydrocarbon in many respects. Like aliphatic hydrocarbon, alicyclic hydrocarbon may be saturated or unsaturated in nature. Saturated alicyclic hydrocarbon are generally known as cycloalkanes. They have the general formula CnH2n and are isomeric with alkenes. In this chapter, we shall discuss the chemistry of cycloalkanes. Nomenclature of cycloalkanes. First is common names. Saturated alicyclic hydrocarbon contain a number of methylene groups joined together to form a ring. Therefore, they are known as polymethylenes in the common system. Accordingly, the individual members are named by prefixing the number of carbon atom in the ring before the word methylene. For example, trimethylene, tetramethylene, hexamethylene. IUPAC system. In the IUPAC system, the saturated alicyclic hydrocarbons are termed cycloalkanes. The individual members are named by adding the prefix cyclo to the name of corresponding starting chain hydrocarbon having the same number of carbon atom as the ring. For instance, cyclopropene, cyclobutane, cyclohexane. Quite often, alicyclic hydrocarbon are also represented by drawing simple geometric figures such as triangle for cyclopropene, a square for cyclobutane, a pentagon for cyclopentane, and so on. The presence of carbon atom at each of the corners and hydrogen atom attached to carbon is taken for granted. For example, cyclopropane, cyclobutane, cyclopentane, cyclohexane. Nomenclature of substituted cycloalkanes. IUPAC name of substituted cycloalkanes are assigned by following the IUPAC rules which the student has already studied. However, some important points are given below. First, for monosubstituted cycloalkanes, there is no need of numbering the indicate position of the group. For example, methyl cyclohexane. For cycloalkanes containing more than one substituent, the numbering of the carbon atom of the ring is done in such a way that the substituent get the lowest possible numbers. Their names are prefixed in alphabetical order along with their position. Moreover, the substituent which comes first in alphabetical order is given the lowest possible number provided it does not violate the lowest set of locant rule. For example, 1,3-dimethyl cyclopentane, 4-ethyl 1,2-dimethyl cyclohexane, 1-ethyl 2-methyl cyclopentane. Third, if the ring contains equal or more number of carbon atom, then the alkyl group attached to it, the compound is named as the derivative of cycloalkane and the alkyl group is taken as the substituent as already shown above. If the ring contains lesser number of carbon atom than the alkyl group attached to it, or if more than one ring is attached to a single chain, the compound is named as derivative of alkane and the alicyclic ring is treated as the substituent. For example, 2-methyl 1-cyclopropyl butane, 1,3-dicyclohexyl propane. In addition to the above rule for cycloalkane, some important points for naming cyclo compound containing multiple bonds and other functional groups are given below. First, if the chain carbon of chain attached to alicyclic ring contain a multiple bond or a functional group, the carbon chain is taken as the parent and the ring is treated as a substituent irrespective of the size of the ring. 3-methyl 1-cyclobutyl but 1-ene, 1-cyclohexyl but 2-one. Second, if the compound contains an alicyclic ring directly attached to a benzene ring, it is named as the derivative of benzene. For example, cyclohexyl benzene 1 bracket start 3-methyl cyclohexyl bracket close 4-nitrobenzene. If the ring contains a multiple bond and the side chain contain a functional group, the ring is treated as a substituent and the compound is named as derivative of chain containing the functional group. For example, 4-cyclohex, 2-ene, YL-butane, 1-ol. Fourth, if the functional group containing carbon is directly attached to alicyclic ring, the carbon atom of this group is suitably included in the suffix used for the group. For example, CHO group is represented by the suffix carbaldehyde, C double bond OH by carboxylic acid, and CN by carbonitrile. For example, cyclopentane carbaldehyde, cyclohexane carboxylic acid. Now, synthesis of cycloalkanes and their derivative. Only method number 3, 5 and 7 are included in the syllabus. The important methods of synthesis of cycloalkanes and their derivatives are discussed below. Most of these methods, it may be noted, involve the conversion of some open chain compound into a cyclic compound through the process of cyclization or ring closure. The cyclic compound thus obtained may be cycloalkanes or its derivative. If required, cycloalkane derivative is further subjected to suitable reaction to change it into the desired cycloalkanes itself. First reaction, addition of carbenes to alkenes. This method involves the addition of carbenes to alkenes to form cyclopropane derivative. The reaction is also referred to the cycloaddition. Since free carbenes are too reactive to be isolated, the reaction is actually carried out by using a carbene precursors that generate the carbene under suitable experimental condition. For example, when treated with diazomethane CH2N2 or ketene CH2 double bond C double bond O. In the presence of light, alkanes add on carbene to form cyclopropane derivative. Alkene plus diazomethane give rise to, in presence of heat, substituted cyclopropane. For instance, 2-butene plus CH2N2 give rise to 1,2-dimethyl cyclopropane. Second reaction, Siemens-Smith reaction. In this method, addition of carbene is carried out by treating the alkene with methylene iodide CH2I2 and zinc copper couple to get cyclopropane derivative. For example, alkene plus CH2I2 in the presence of ZnCu give rise to substituted cyclopropane plus ZnI2. Zn copper couple required for the reaction is usually obtained by heating zinc dust with CuCl in ether in the presence of nitrogen. It is believed that methylene iodide and zinc react to form carbene-like species called carbenoid. It is believed that CH2I2 plus zinc copper give rise to ICH2ZnI, iodomethylene zinc iodide, also known as carbenoid. The carbenoid brings about the stereospecific addition of CH2 group directly to the alkene. Siemens-Smith reaction gives better yield of cycloalkane than is obtained by the addition of free carbene to alkene. Third is photochemical 2+2 cycloaddition reaction. The term cycloaddition denotes an addition reaction between two unsaturated molecules to form a cyclic product. During these reactions, new sigma bonds are formed at the cost of pi bonds of reacting molecules. Individual reactions are designated by writing the number of pi electron of each reactant in the square brackets. For example, a reaction between two alkene molecules to form a cyclobutane ring by using 2 pi electron of each molecule is referred to as 2+2 cycloaddition. 2+2 cycloaddition reaction can be carried out easily in the presence of light, but not under thermal conditions. Such reactions are termed as photochemical 2+2 cycloaddition reaction. They take place by the concentrated mechanism involving cyclic transition state. The form of substituted cyclobutane by photochemical 2+2 cycloaddition of two alkene molecule may be represented in general as follows. Alkene, in the presence of heat, gave rise to cyclic transition state, give rise to substituted cyclobutane. For example, ethylene in the presence of light gave rise to cyclobutane. Fourth, 4 plus 2 cycloaddition, Diels-Alder reaction. 4 plus 2 cycloaddition reactions involve the addition of an alkene, 2 pi electron, referred to as diphenyl and conjugated diene, 4 pi electron, to form 6-membered system. In contrast to 2 plus 2 cycloadditions, these reactions take place readily under thermal condition. For example, 1,3-butadiene plus ethene give rise to cyclohexane. If the diphenyl contain electron attracting groups such as C double bond O, C double bond OH, Cn, Cl, the reaction take place extremely easily, sometime even at room temperature. For example, 1,3-butadiene plus CH2CH plus CHO in the presence of 373 Kelvin temperature give rise to 1,2,3,6 tetrahydrobenzyaldehyde. It is interesting to note that 2 plus 2 cycloaddition reaction take place readily photochemically but not thermally. On the other hand, 4 plus 2 cycloaddition reaction occur readily thermally but not photochemically. Fifth, dehalogenation of suitable dihalogen derivative of alkanes. Freund's method. On treatment of suitable alpha omega dihalogen derivative of alkane, it means dihalogen derivative having the halogen atom attached to a terminal carbon atom with sodium or zinc, they get dehalogenated to form cycloalkanes. For example, 1,3-dibromopropane plus zinc give rise to cyclopropane plus ZnBr2. 1,4-dibromobutane plus zinc give rise to cyclobutane plus ZnBr2. The method may be regarded as the internal Woods reaction. However, this method gives good yields only in the preparation of cyclopropane. If the alpha-omega dihalide contain more than 6 carbon atom, intermolecular Woods reaction take place, giving rise to an open chain alkane. Sixth method is Dickmann's cyclization. When ester of certain dicarboxylic acids such as adipic acid and pimelic acid are treated with sodium or sodium ethoxide, they undergo intermolecular Clanson condensation to yield cyclic B-keto esters. The beta-keto esters on hydrolysis and heating get decarboxylated to form cyclic ketones. The ketones are in turn subjected to Clanson reduction to get cyclic alkanes. For instance, adipic ester plus Na give rise to 2-carbo-ethoxy cyclopentane 1-on. In the presence of H2H positive give rise to 2-carboxy cyclopentane 1-on. In the presence of heat give rise to cyclopentane 1-on, and in the presence of ZnHgHCl give rise to cyclopentane. Dickmann method is most suited to the preparation of 5 and 6-membered ring. 7th, pyrolysis of calcium or barium salt of dicarboxylic acid, Wieslenz's method. When the calcium or barium salt of certain dicarboxylic acids are heated strongly, they yield a cyclic ketone. The ketone thus formed is converted into cycloalkane through Clanson reduction as illustrated below. Calcium adipate in the presence of heat gave rise to cyclopentane 1-on. In the presence of ZnHgHCl gave rise to cyclopentane. In keeping with Blank's rule given below, this method is used for the preparation of 5 and 6-membered ketone. Blank's rule. This rule was formulated by Blanks on the basis of experimental observation of the ease of formation of cyclic anhydride and ketone by distillation of dicarboxylic acid according to relative position of 2 carboxylic group. According to this rule, distillation of 1,4 and 1,5 dicarboxylic acids give rise to cyclic anhydride, while 1,6 and 1,7 dicarboxylic acid yields ketone. 1,8 and higher dicarboxylic acid remain unaffected. Blank's rule can be used for determining the size of ring as well as the chain length of the dicarboxylic acid. For this purpose, a double bond is introduced by suitable method in the given compound whose ring size is to be determined. The unsaturated The unsaturated compound thus obtained is subjected to oxidative cleavage with KMnO4 to get a dicarboxylic acid. This acid is heated with acetic anhydride and distilled. If a cyclic anhydride is obtained as a product, the acid is either 1,4 or 1,5 in nature. If a cyclic ketone is formed, the acid has 1,6 or 1,7. If there is no change, the acid is 1,8 or higher. The structure of the acid in turn reveals the size of the ring. Eighth reaction, Thorpe-Ziegler reaction. On heating in the presence of lithium diethylamide C2H5 twice, N negative Li positive, and alpha omega dinitrile, a nitrile in which the nitrile group are attached to the terminal carbon atom, undergo intermolecular condensation to form a cyclic aminonitrile. This is changed into cycloalkane as illustrated below. Alpha omega dinitrile in the presence of C2H5 twice and negative Li positive give rise to aminonitrile. In the presence of H2H positive give rise to ketoacid. In the presence of heat give rise to ketone, and in the presence of ZnHgHCl give rise to cycloalkane. The first step in the reaction involving cyclization takes place only at very high dilution. It is referred to as Ziegler-Thorpe high dilution technique. Thorpe-Ziegler reaction is particularly suitable for the preparation of higher ring compound. Demensov rearrangement. This reaction provides a method of expanding and contracting alicyclic ring system through the formation of carbocation. The carbocation themselves are obtained by the demethylation of alicyclic amine by treatment with nitrous acid. Once formed, the carbocation undergo its characteristics reaction. This is addition of nucleophile, elimination of a proton, rearrangement to a more suitable carbocation. As a result, different products are formed including ring expansion or ring contraction product as illustrated below. Ring expansion. When cyclobutyl methylamine first is treated with nitrous acid, we get 4 products. Cyclobutyl carbinol third and methylene carbobutane second are formed without involving any ring expansion. At the same time, cyclopentanol fourth and cyclopentene fifth are formed by ring expansion as below. Ring contraction. When cyclobutylamine 6th is treated with nitrous acid, cyclobutanol 8 is formed without any ring contraction. At the same time, cyclopropyl carbonyl 8 is formed by the ring contraction. It may be noted that when the carbocation initially formed carried the positive charge on the alicyclic carbon, it leads to ring contraction. On the other hand, when the initially formed carbocation carries the positive charge on the carbon alpha to the alicyclic ring expansion takes place. Hydrogenation of aromatic compound. Cyclohexane and its derivatives can also be prepared by the hydrogenation of benzene and its derivative. For example, benzene plus 3H2 give rise to cyclohexane. 11th, condensation of suitable dihalide with malonic ester or acetic ester followed by hydrolysis and decarboxylation. In the presence of sodium ethoxide, active methylene compounds such as malonic ester and acetoacetic ester condense with suitable dihalide to form cyclic diester. These on hydrolysis and decarboxylation yield cycloalkanes. For instance, ethylene dibromide malonic ester plus 2CH2 H5O negative Na positive give rise to cyclopropane dicarboxylic ester. In the presence of H2H positive give rise to cyclopropane dicarboxylic acid, and in the presence of heat give rise to cyclopropane monocarboxylic acid. Cyclopropane monocarboxylic acid is then converted into cyclopropane through a sequence of reaction. It may be noted that this acid cannot be directly decarboxylated by heating as it's led to cleavage of the ring. Acetoacetic ester may also be used in the place of malonic ester in this reaction. The ketone obtained above is suitably treated to get the corresponding hydrocarbon. Physical properties. In their physical properties, cycloalkanes resemble the corresponding open chain compounds, although they have somewhat higher boiling point and densities. For instance, the first two members of cycloalkane, cyclopropane and cyclobutane, are gases, while higher members are liquid. Second, they are non-polar in nature and as such insoluble in water but soluble in organic solvents. Some of them, such as cyclohexane, are good solvent themselves. Chemical properties. The general chemical behavior of cycloalkanes is similar to that of corresponding open chain hydrocarbon. Like alkane, cycloalkanes also contain only carbon-carbon single bond and carbon-hydrogen sigma bond and are therefore quite inert towards chemical reagent and undergo only a few substitution reactions. It must be emphasized, however, the cyclopropane and cyclobutane differ considerably from their higher homologues. This is because the cyclopropane or cyclobutane rings are not very stable and have a tendency to open form and form addition product. As such, these resemble alkanes in undergoing some addition reaction, but they are less reactive than corresponding alkane. A few reactions of cycloalkane are described below. First is reaction with halogens. Generally speaking, cycloalkanes undergo free radical substitution with halogen at high temperature or in the presence of light. For example, cyclohexane plus Br2 in the presence of light give rise to bromocyclohexane. Cyclopropane plus Cl2 in the presence of light give rise to chlorocyclopropane. In case of cyclopropane, however, bromide and chloride break the ring system in the presence of FeBr3 or FeCl3 and high temperature and yield open chain addition product. For example, cyclopropane plus Br2 in the presence of FeBr3 give rise to 1,3-dibromopropane. Second, reaction with halogen acid. In general, cycloalkane do not react with halogen acid. However, cyclopropane adds on halogen acid to form open chain alkyl halide. Cyclopropane plus HI give rise to N-propyl iodide. Cyclopropane plus HBr give rise to N-propyl bromide. Cyclohexane plus HI give rise to no reaction. Third, addition of water. When heated with concentrated H2SO4, cyclopropane but not other cycloalkanes add on water to form an alcohol. Cyclopropane plus H2O give rise to H2SO4. In the presence of H2SO4 give rise to N-propyl alcohol. Fourth, reaction with hydrogen. When heated with hydrogen in the presence of nickel, cyclopropane and cyclobutane form open chain addition product, while higher cycloalkanes do not react. Reaction of cyclobutane take place at much higher temperature than required in the case of cyclopropane. Cyclopropane plus H2 in the presence of nickel and the temperature 373 Kelvin give rise to N-propane. Cyclobutane plus H2 at very high temperature give rise to butane. Cyclohexane plus H2 give rise to no reaction. It may be noted that of the cycloalkane, cyclopropane is the most reactive since it undergoes many addition reactions accompanied by ring cleavage. Next comes cyclobutane, which undergo addition of hydrogen, while the rest of cycloalkane do not form addition product. Relative stabilities of cycloalkanes. Bayer's strain theory. During the earlier stages of their study, cycloalkane containing up to only 6 carbon atom ring could be prepared in the laboratory and the ring containing 7 or more carbon atom were unknown. It was also observed quite early that like open chain alkane, cyclopentane and cyclohexane are quite stable and do not undergo addition reaction. On the other hand, cyclopropane and cyclobutane were found to be relatively much less stable and capable of undergoing even addition reactions through ring cleavage. The difference in the relative stabilities of different cycloalkanes was initially explained in the term of Bayer's strain theory as discussed below. Bayer's strain theory. According to tetrahedral concept of carbon, a carbon atom bounded to 4 other atoms lies at the center of a tetrahedron and the angle between any two bonds is 109 degree 28 minutes. Adolf von Baer 1885 argued that any departure from their position leads to a strain in the molecule, as a result of which the stability of the molecule decreases. On this, Baer proposed a theory known as Bayer's strain theory. The important points of this theory are: first, the carbon atom constituting the ring lies in the same plane. Consecutively, the bond angle between the adjacent carbon atom of the ring no longer remain 109 degree 28 minutes, which is the normal bond angle of the tetrahedral carbon. On the other hand, different rings have different value of this angle. For instance, the cyclopropane ring is a triangle having carbon single bond carbon angle of only 60 degree. Second, any deviation positive or negative from the normal tetrahedral bond angle of 109 degree 28 minute during the formation of ring product an internal strain in the resultant molecule which make the molecule unstable. Positive deviation means the angle is compressed while negative deviation means the angle is expanded. Third, the greater the deviation from the normal angle, the greater is the strain and therefore the lesser is the stability. It may be noted, however, that the sign of deviation makes no difference. Fourth, the more the stable of the ring system, the more easily it is formed. Bayes calculated the deviation from normal angle or what makes the called angle strain involved in the formation of cycloalkanes of various ring size. For example, the carbon single bond carbon angle of the cyclopropane ring in 60 degree. Since each carbon atom occupy a corner of an equilateral triangle, this means that angle strain in cyclopropane would be 1 by half of 109 degree 28 minute minus 60 degree or 24 degree 44 minute. Similarly, the angle in cyclobutane is 90 degree as each carbon atom is situated at the corner of a square. As such, the angle strain in cyclobutane is half of 109 degree 28 minute minus 90 degree or 9 degree 44 minute. The angle strain of cyclopentane is 0 degree 44 minute, cyclohexane is minus 5 degree 16 minute, cycloheptane is minus 9 degree 33 minute and cyclooctane is minus 12 degree 46 minute. Evidence in the favor of Bayes strain theory. It is obvious from the bond angle that the magnitude of the strain goes on decreases as we proceed from cyclopropane to cyclopentane. Hence, ease of formation and stability should show a corresponding increase. This is actually found to be so. The ease of the formation and stability of cyclohexane could also be justified in the view of small angle strain in this case. The fact that cycloalkane have 7 or more carbon atoms were not known to exist at the time of Bayes was attributed to be increasingly large strain in the formation of higher ring. Second, Bayes strain theory could also account for the great reactivity of ethylic bond. The double bond was treated as a two-membered ring in which the angle strain is half of 109 degree 28 minute minus 0 degree or plus 54 degree 44 minute. This large strain seems to be responsible for the reactivity of double bond. Limitation of Bayes strain theory. Bayes strain theory failed to explain the following. First, ease of formation of ethylenic bond. The ethylenic bond can be formed readily in spite of having such a large angle strain. Stability of cyclohexane and higher cycloalkanes. Heat of combustion of cycloalkanes. Bayes strain theory failed to explain the stability of cyclohexane and higher cycloalkane as discussed below. Cyclohexane and higher cycloalkane, many of which was prepared after Bayes strain theory had been proposed, are found to be nearly as stable as cyclopentane as shown by their heat of combustion. The heat of combustion per methylene group CH2 of various cycloalkane are given in table 4.2. Size of the ring is 3, heat of combustion is 697. Size of the ring is 4, heat of combustion is 686. Size of the ring is 5, heat of combustion 664. Size of the ring 6, heat of combustion is 658.5. Size of the ring is 7, heat of combustion is 662.3. Size of the ring is 8, heat of combustion is 663.6. Size of the ring is 9, heat of combustion is 669.4. Size of the ring is 10, heat of combustion is 663.6. Size of the ring is 11, heat of combustion is 662.7. Size of the ring is 12, heat of combustion is 659.3. Size of the ring is 13, heat of combustion is 660.2. Size of the ring is 14, heat of combustion is 658.5. Heat of combustion per CH2 group of open chain alkene is 658.5 kJ per mole. The heat of combustion per CH2 group gives a fair idea of relative stability of cycloalkane since each CH2 group yields only carbon dioxide and water on combustion. If the heat of combustion is large, the compound contains more energy and therefore less stable and vice versa. It is immediately apparent from table 4.2 that as compared to open chain alkene, cyclopropane and cyclobutane give out nearly 38 and 28 kilojoule more energy per CH2 group. This means that they are relatively less stable, a fact which is an agreement with Baer strain theory. However, the heat of combustion per CH2 group of cyclopentane and cyclohexane and higher cycloalkane differ only very slightly from that of the open chain alkene. This implies that cyclopentane and higher ring alkane were nearly as stable as compared to open chain alkene. This obviously goes against Baer theory, according to which cycloalkane have more than 5 carbon atom ring should be increasingly less stable due to increasing deviation from the normal tetrahedral angle. More theory of stainless ring. To explain as to why cycloalkane having ring of 6 or more carbon atom are almost as stable as cyclopentane, Sachs 1890 put forward a theory of stainless ring for higher ring compound. According to him, carbon atom containing the ring lies in the same plane only up to 5-membered ring, while the carbon atom in 6-membered ring and higher ring do not lie in the same plane. Since the carbon atom in the 6-membered and higher ring lie in different planes, the normal tetrahedral angle remain unaltered. As such, there is no angle strain in bigger rings, and that is why they are stable. For instance, Sachs proposed the existence of two types of multiplanar or puckered stainless rings known as chair and boat form for cyclohexane. Both these forms are free from angle strain and can be interconverted just by rotated around single bonds. Thus, they merely represent two conformations of cyclohexane and cannot be isolated separately. Similarly, 7-membered and higher rings are stainless in nature. Sachs' theory of stainless rings was further supported and elaborated by Moore 1918 to cover the compound containing two rings fused together. Difficulty encountered in the synthesis of large membered ring. It may be interesting to note as to why bigger rings are rather difficult to synthesize even though there is no angle strain in them. This is primarily due to the fact that two ends of the chain of atom must come close together for ring closure to take place through interaction between the group present at the two ends. If the chain undergoing ring closure is very long, there are relatively lesser chance of the two ends coming close enough for the ring to be formed. On the other hand, what may happen is that the end of one chain may interact with the end of other different chain, leading to the formation of an entirely different product. This difficulty is now being overcome by carried out ring closure reaction in highly dilute solution. Under these conditions, collision between different chains are minimized and the ring closure take place as the main reaction, although at very slow rate. But once the rings are formed, they are quite stable. Bent or banana bond in cyclopropane, orbital picture of angle strain. According to orbital concept of covalency, a covalent bond can be formed between two atoms only if these atoms are oriented in such a way that their orbitals can overlap each other. It may also be recalled that the greater the overlapping of atomic orbitals, the stronger the bond formed. Now the carbon atom of cycloalkane are in the state of sp3 hybridization, and the formation of a covalent bond between two such atoms involves the overlap of an sp3 orbital of one carbon atom with a similar orbital of the other. For maximum overlap, the bonding should take place in such a way that bonding orbital point directly towards each other. Consecutively, when carbon is bonded to two other carbon atom, the carbon single bond bond angle should be 109 degree 28 minute. But in cyclopropane, the bond angle is only 60 degree. This means that in cyclopropane, the bonding orbital are not pointing directed towards each other along a straight line. As a result, the overlap of these orbitals take place to a very small extent and the bond form are described as bent bond. These bonds are much weaker than the normal carbon-carbon bonds. Consecutively, the cyclopropane molecule is quite unstable or strained and reactive in nature. In cyclobutane, carbon single bond angle is 90 degree. The overlap is relatively more affected than in cyclopropane. As such, cyclobutane is relatively more stable. Thank you.